Swayam Prabha. Digital India. Educated India.
In the previous module, we saw the basic requirements for an estimate to be a good estimate. We talked about unbiasedness, we talked about relative efficiency, we talked about consistency, we also talked about sufficiency. We did not cover sufficiency much, but we gave a view of what sufficiency deals with. So what is that we are looking for? We are looking for estimates that are unbiased, consistent, efficient estimates, and in some cases we don't have to throw away the bias estimate because we have shown that there is a trade-off, bias versus variance. There are estimates which are not unbiased, that means there are biased estimates which are more efficient. So it all depends on what is that you are willing to tolerate. You are willing to tolerate a little bit bias, but having more efficiency, so you can have a variety of different choices possible. Now, I am going to revisit the least squares, not the deterministic, but the statistical version of least squares. There are some very fundamental results that the deterministic theory does not give rise to, but the statistical theory does. So we are going to the new add-on to the theory of least squares coming from statistical perspective. Again, I am going to be using linear least squares. There is also corresponding statistical nonlinear least squares. So z is equal to h of x plus v. So plus v is the new thing. So z is Rn, z is Rm, x is Rn. So you simply again have Rn to Rm, and h is the mapping from Rn to Rm. V is the associated noise affecting the observation. In the deterministic case, we assume that there is no V, and we have calibrated my meters such that E of V is 0. The covariance of V transpose, V is a column vector. So please understand, V is also a M vector. Therefore, R is a matrix, covariance matrix. R is a M by M matrix. I am assuming R is an SPD matrix. And we already talked about this SPD matrix could be a dense matrix, could be a diagonal matrix, or could be a diagonal matrix with a constant diagonals. The reciprocal of R is called the information matrix. So let's look at the meaning of R inverse. Let's assume R is equal to sigma 1 square, sigma 2 square. Let's assume the case of M is equal to 2. Sigma 1 square is the variance of the first component of Z1, sigma 2 square is the first component of the variance Z2. So what is R inverse? R inverse is equal to sigma to the power minus sigma 1 square to the power minus 2. This is sigma 2 square to the power minus 2. That means the reciprocal. So if sigma 1 square is large, the reciprocal is small. I'm sorry, that probably a better way would be to write it like this. 1 over sigma 1 square, that's much simpler. 1 over sigma 2 square. So if sigma 1 square is large, the reciprocal is small. If sigma 2 square is large, the reciprocal is small. That means if the variance is large, I have much less information. If the variance is small, I have more information. If I have more information about a particular quantity, I would like to give more emphasis to that quantity. than the one that contains less information. For example, when you have friends, some friends are more reliable than others. So if you know your friend A is more reliable, you always listen to him as to what his opinions are. You give more weight to him. So in this case, statistical least squares naturally leads to weighted least squares, where R inverse is going to be used as a weighting matrix or the weight function. Here we are also making a fundamental assumption that X and V are not correlated. If X and V are correlated means what? My measuring instrument is affecting the mother nature. Please understand, when you are trying to take blood pressure, your blood pressure instrument, the instrument that measures the blood pressure should not change the blood pressure too much. That's an important thing. So the measuring instrument must not affect the process being measured. So that essentially is translated mathematically into X and V are uncorrelated. So these assumptions are common. We have already talked about these assumptions earlier as well. I now talk about the residual. Here again, I have two cases, m greater than n, m less than n. With a loss of generality, I am going to assume m is greater than n. So consider an overdetermined linear least square problem where the observations are noisy. The observation noise is Gaussian with mean 0 and the covariance R. R inverse is called the information matrix. In general, the residual cannot be made 0. So I am going to consider the weighted sum of squared residual, that is f of x. R transpose R is the unweighted sum of squared residual. R inverse is the weight. So this weight is the information matrix. Now, as I already told you earlier, I want to give more weight to the one that is more informative and less weight to the one that is less informative. And there's a very natural way of weighting the sum of square residual, and you can really see this is also equivalent to the energy norm with respect to the matrix R inverse. You remember the energy norm is X transpose AX, and that is often expressed as square A. This is what we saw when we talked about linear vector spaces. So linear vector space theory and statistical estimation and minimization techniques all come together. And that can be expressed as this term. So f of x is the weighted sum of squared errors. The weighting function comes naturally from the information matrix relating to the observation noise. So now you can readily see a natural way to pick up the weighting matrix as the information matrix associated with the observation noise. Now I want to be able to minimize this. I'm going to compute the gradient. I'm going to compute the Hessian, which we have already done. So this is the expression for the gradient. This is the expression for the Hessian. The least square estimate is obtained by solving this equation, normal equation in this case. Normal equation is H transpose R inverse H of x is equal to H transpose R inverse Z. Therefore, XLS is equal to H transpose R inverse H inverse H transpose R inverse Z. And that's exactly the relation 3. So this is the least square estimate that corresponds to this. This I can express this as H plus Z with R. H plus Z with R is essentially the generalized inverse of that. So this I can rewrite as H plus R inverse Z, where H plus R inverse is equal to H transpose R inverse H inverse H transpose R inverse. So this is the generalized inverse weighted by R inverse. From here, I can also get the projection matrix. The projection matrix is PH R inverse. This is equal to HH plus. So this is the oblique projection. It is idempotent but not symmetric. Please verify. This is idempotent, not symmetric. Not symmetric. So all the theory applies. So what is the only difference? In the earlier case, we simply dealt with the weighted case to obtain oblique projection. Now I am giving little life to the concept of weighting. The weighting comes through the information matrix associated with the observational errors, which is a very natural form of weighting. Now I am going to, okay, so let's go back now. Xs is a linear function of z, and z is random. Therefore, XLS is random. Okay, that's something new. So this is random. Therefore, the estimate is also random. If the estimate is random, I now need to be able to bring this estimate under the umbrella of the statistical estimation technique. So the first thing I need to worry about is this estimate unbiased? So z is equal to h of x plus v. If you substitute this z in here and simplify, you can readily see the least square estimate is equal to the original unknown plus a perturbation term that is coming out of the noise term. This perturbation term coming out of the noise term is a linear map of the observation vector. So if I took the expected value of the estimate is equal to x plus the expected value, this time the expected value of v, but v is mean 0, so this, the expected value of this is equal to 0, becomes unknown, so that is unbiased. Therefore, the least square estimate, the weighted least square estimate is an unbiased estimate. That's the first result. Now, I would like to be able to compute the covariance of the estimate. Variance, covariance. We talk about variance for the case of scalars, covariance for the case of vectors. The sum of the diagonal elements of the covariance matrix is called the total variance. So, I want you to understand various terms now. Variance of a random variable x, covariance of a random vector x, and also the total variance. The total variance is equal to trace of the covariance matrix. Covariance matrix of x. Covariance matrix of x, trace of covariance matrix is the sum of all the diagonal elements. So, variance, covariance, and the total variance. These are the three quantities that we will be dealing with. The covariance of the estimate is covariance of x hat ls. We already know its true mean is x. And you already know the definition. The covariance must be equal to the covariance of a vector x must be equal to expected value of x minus e of x times x minus e of x transpose. That's the definition of a covariance matrix. So this is the column, this is the row, that's the matrix here. So according to that definition, this is the covariance matrix, this is the outer product, expected value is the outer product. I now have an expression for xls minus x. xls minus x is equal to is given by this expression. And that expression is now being substituted in here. This expression is substituted here. This expression is substituted here. And that expression has a matrix which is constant. That expression has a matrix which is constant. So if I did suppose substitute and take the transpose of this, you can readily see this factor comes out, this factor comes out, this is the middle one. And this is equal to R. R inverse will cancel. Then H transpose R inverse, H transpose R inverse, H inverse, they will cancel each other, leaving behind only one term, which is H transpose R inverse, H inverse. So what is this? This quantity is related to the Hessian. Equation 2, what is that? That the Hessian of f of x, please understand, f of x is given by this expression, which is star the Hessian of that is H transpose R inverse H. So this is H transpose R inverse H inverse. So this is the inverse of the Hessian. Inverse of the Hessian. So if the Hessian is positive definite, its inverse is also positive definite, covariance will be positive definite. Or to look at the other way, if the covariance of the estimate is positive definite, the Hessian is also positive definite. If the Hessian is positive definite, the minimum is unique. That's the idea. The convexity condition applies. The cost function f of x has a unique minimum. Now I am going to talk about projection. So look at this now. Please remember this. This is the span of H. Span of H means span of the columns of H. This is Z. This is, in this case, this is bias test. I'm sorry. This is the oblique estimate. This is Z hat. Z hat is a vector along the span. So Z hat must be equal to H of XLS. Z hat is equal to H of X ELS. So Z hat is equal to H of XLS. XLS, I know what it is. I substitute this. This becomes P of Z. P is called the projection matrix. So the projection matrix is the oblique projection matrix, which is given by that. I want you to verify projection matrix is idempotent. It is not symmetric. B is a oblique projection. When R inverse is I, what do you mean by R inverse is I? The covariance matrix of the noise is an identity matrix, then this becomes a symmetric, in which case it becomes an orthogonal projection. So it is the property of the observation noise covariance that decides the projection to be oblique or orthogonal. Now I am going to talk about observations that are uncorrelated. That means R is equal to sigma square I. That's exactly what I told you earlier. Look at this now. This is R. R has a diagonal, off-diagonal entries. Off-diagonal entries relate to cross-correlation of the noise affecting the different components of the vector Z. So Z is equal to the vector Z1, Zi, Zj, and Zm, let us say. If I and J are correlated, there will be a non-zero quantity here, non-zero quantity here, which is the ijth element, jth element of R. So if the observation noise affecting the different components of the vector Z are uncorrelated, then this is 0, this is 0. That's the diagonal matrix, and I am assuming the diagonal matrix has the same diagonal elements across the diagonal, sigma square. So R is equal to sigma square I. In this particular case, XLS is equal to the value of the least square estimate in the unweighted case. So when the noise is uncorrelated, when the diagonal elements are the same, I get the old deterministic result. So then the statistical result coincides with the deterministic result in this special case. Now I can talk about a couple of other properties. We know lots about matrices now. We also know H transpose H is symmetric. I am assuming M is greater than N. I am assuming H is a full rank matrix, rank of H. Rank of H is equal to N. That's my full, N. Rank of H is equal to N. I am assuming it's a full rank matrix. Rank of H is N. So H is symmetric, is a full rank matrix. Therefore, H transpose H is a symmetric positive definite matrix. I can do an eigen decomposition of H transpose H. I am going to call it the columns, the eigenvectors are the columns of Q. Earlier I had called it V. Now I am calling it Q. After all, the concept is the same, the representation may be due to different, I can use different symbols to do that. So H transpose Q is equal to Q lambda. So H transpose H is equal to Q lambda Q transpose, and these two are orthogonal matrices. Lambda is a diagonal matrix, and HH transpose is equal to Q lambda inverse Q transpose. Why am I going this way? Please understand the covariance of the statistical least square when the noise covariance is a diagonal matrix with the same diagonal elements is related to inverse of H transpose H. So I would like to be able to compute H transpose H and its inverse, and that's exactly what I have done here. So this is Q lambda inverse Q transpose. Now please understand, I talked about the trace of the covariance of the XLS hat. So this is the random estimate. Every random estimate is a estimate of the random vector. It is a covariance matrix of that. Trace of that is equal to the total variance. Please understand, this is the variance of the total. Is the sum of all the diagonal elements, which is the trace. So this is the trace of the covariance is equal to sigma square H transpose H. That is substituted here. Sigma square is a constant. I can take it out of the trace. Trace of Q lambda inverse Q transpose. And please remember, trace of ABC is equal to trace of CAB, which is equal to trace of BCA. Using this formula, I can rewrite this by rotation. Look at this now. This is a right circular rotation. So I have ABC. So ABC, BCA, CAB. It rotates like this, and all the traces are equal. ABC, BCA, CAB, they are all equal. So using that, I can rewrite this with Q transpose Q as Q times lambda inverse. But Q transpose Q transpose is identity. So that becomes trace of lambda inverse, and lambda inverse is the diagonal matrix. So that is equal to sigma square, the sum of the reciprocals of the eigenvalues of the Gramian, the smaller the Gramian, H transpose H. So lambdas are the diagonal elements of the matrix lambda, which are the eigenvalues of the smaller of the two Gramian, H transpose H. Now look at this now. This eigenvalues is SPD, right? So this is the real axis, this is the imaginary axis. Being SPD, the eigenvalues are real. The eigen may be real, but lambda n, which is the smallest eigenvalue, can be very close to 0. If the smallest eigenvalue is very close to 0, it's very nearly singular. That means 1 over lambda becomes very large. See, so if the eigenvalues are very close to 0, what does this tell you? The total variance, which is the trace of the covariance, becomes large. If the variance becomes large, means what? The estimate is unreliable. The estimate has a lot of spread. The estimate has a lot of spread. So in the earlier case, we talked about H transpose H being nearly singular. Nearly singular means what? The columns, at least a pair of columns of H are very nearly collinear. The angle between them is close to being 0. There the condition, we call it ill condition. That's relating to collinearity of the columns of H, can lead to ill-posedness of the problem. Here we are explaining the same situation using a different approach. In the statistical case, I am computing the total variance, which is the sum of the variance of the estimates of all the components of Excel least square estimate x hat ls. The covariance could be large. If the covariance estimate is large, we know it is not efficient. So I lose efficiency in the statistical context if there is collinearity between the two columns of H. Collinearity between the two columns of H is going to be reflected as the eigenvalues, the smallest eigenvalue of the Gramian, smaller of the two Gramian, H transpose H, is being close to 0. So I would like you to be able to relate all these quantities. Now, I assumed in this analysis sigma square is known. So suppose sigma square is not known. Let's go back now. What is sigma square? Sigma square is the variance of the noise that affecting the observation. Generally, sigma square we assume to be known. It comes from the properties of the instrument that is used to measure. Suppose the instrument is very old and has lots of calibration. I would like to be able to estimate sigma square. So in such case, I would like to be able to estimate sigma square. That means I can use the least square method to be able to estimate the noise covariance or the noise variance. So I am assuming R is equal to sigma square I. So knowing sigma square is equal to knowing R. I would like to be able to estimate this unknown sigma square. Please understand, we are doing statistics, we are doing estimation. I can do lots of different estimation. This known, that not known. This known, that not known. Nothing is known. So there are a whole family of methods depending on what is known and what is not known. So we did an analysis conditioned on sigma square is known. Now, if sigma square is not known, how am I going to estimate that? To that end, I am now going to consider the residual. Please understand, z hat is the estimate of z. You remember z hat from the oblique projection. The slide in the picture in slide 5, z hat. Just to be able to tell you again, this is the span of h. That is z. This is z hat. So this is the residual. So the residual, in this case, I am simply calling it E. Sometimes I call it R, sometimes I call it E. The notation should not bother us. So z minus h of xls hat, this is I minus p times z. Z is equal to h of x plus v. So I minus p times h of x plus I minus p times v. So, but I want you to recognize one thing. I minus p times h is equal to h times ph. And what is p? P is equal to h transpose, h inverse, h transpose. Therefore, ph is equal to h transpose, h inverse, h transpose, h. These two cancel each other. So this is equal to h. So p of h is equal to h. H minus h is 0. Therefore, I minus p times h is 0. If I minus p times h is 0, I have only having the second noise term in here. So the residual E is purely a function of the noise. Purely a function of the noise. So expected value of E is equal to expected value of I minus times V, I minus times expected value of V, that is 0. So the residual has expected value of 0. Now, I am going to estimate sigma square. Sigma square is the sum of the trace of the covariance matrix. So E transpose is a matrix, E transpose E. So I'm going to give you an example now. Let's suppose E is a vector AB. E transpose is AB, which is equal to A square AB, BA, B square. If you have E transpose E is equal to AB, which is equal to A square plus B square. Therefore, you can readily see trace of E transpose is equal to E transpose A. I hope you are all with me now. Therefore, if I am interested in computing the trace of the covariance is equivalent to computing E transpose E. E is random, so I am going to compute the expected value of this random quantity. We already know E is equal to I minus P times V. So substituting that, this is V transpose I minus P. Now please remember, I minus P transpose is equal to I minus I transpose minus P transpose. I transpose is I, P is orthogonal projection matrix in this particular case. Why is the orthogonal projection matrix? Because I have assumed R is sigma square I. And we have already seen in this special case that the oblique projection becomes orthogonal projection. The orthogonal projection matrix is symmetric. So this is I minus P. So I minus P transpose is I minus P because both P and I are symmetric matrices. I also want you to remember one more. P square is P. Therefore, I minus P square is equal to I minus P times I minus P. Let's calculate that. That's equal to I minus P plus P square. But P square is P is idempotent. Therefore, it's equal to I minus P plus P. These two get cancelled. This is I minus P. So, if P square is idempotent, I minus P is also idempotent. Therefore, this I minus P square becomes I minus P. V transpose I minus P times V. This is a scalar. Please understand that trace of a scalar is itself. We have used several facts. A is equal to A transpose. A is equal to trace of A. We can use these facts to simplify. Trace of A is the A. A is A transpose. So this is a scalar. So it is equal to trace of itself. But these are matrices. Trace of the product, trace of ABC is a trace of BCA is trace of CAB. Using that formula, I can get this is VV transpose that. Expected value of trace is equal to trace of the expected value. They commute. So using that rule, I can get from here. So I can take I minus P out. I'm sorry. So this step is equivalent to. So this step is equivalent to what is that? That is the trace of expected value of VV transpose times I minus P. That's a good simplification involved in here. I minus P is a constant. Therefore, this is a trace of E of VV transpose times I minus P. But VV transpose, that's equal to, so this is equal to trace of VV transpose is sigma square I times I minus P. Sigma square times I minus P. And that's equal to sigma square times trace of I minus P. So this sigma square times trace of I minus P, that's a non-trivial algebra involved. There is a non-trivial algebra involved. So this is equal to sigma square times the trace of A plus B is trace of A plus trace of B. So this is trace of A minus trace of P. Now, what is the trace of P? Let's look at this now. Let's come in here. P is H transpose H inverse H transpose. Trace of ABC is trace of BCA, trace of CAB. So trace of P is equal to trace of this. By using that ABC, BCA and CAB, I can rewrite this. These two cancel each other. These two cancel each other. Therefore, H transpose H is a n by n matrix. So this is identity. This is a trace of identity. So the trace of P is n, trace of I is m. So this is sigma square times mn. That means the expected value of E transpose E is equal to sigma square mn. Therefore, the estimate of sigma square, which is given by this estimate, is an unbiased estimate of sigma square. It's an unbiased estimate of sigma square. So if I have a linear least square problem I can have two versions. One, assume sigma square is known, do the analysis. And using the same analysis, I can also use the least square estimate to be able to estimate the variance of the observation noise under the assumption that R is sigma square I. That's an important conclusion. Now I am going to talk about the properties of least square estimate. So I talked about the properties of statistical least squares, statistical linear least squares. So statistical linear least square becomes a weighted least square estimation. The estimate is unbiased. I computed the variance. The variance is related to the inverse of the eigenvalues. So if the eigenvalues are the smaller the true Gramian, so if the smaller the Gramian is very nearly singular, the variance of the estimate is going to be large. Now I am going to talk about other properties of the least square estimate. Please recall, an estimate can be unbiased. The estimate can be linear. So the linearity is one property, unbiasedness is another property. So the set of all unbiased estimate is given in green. The set of all linear estimate is given in orange. The intersection of the two is called linear unbiased estimate, L and U. So LUE means an estimate which is simultaneously linear and unbiased. I always want the best estimate. What is the best estimate? An estimate is said to be a best estimate if it is more efficient. Efficient means what? The variance is less. So blue is called the best linear unbiased estimate. So among all the linear unbiased estimate, I am interested in getting the blue. The blue is a very desired estimate. So in many of the statistical problems, we will always try to seek the best linear unbiased estimate, blue. We have already shown that the least square estimate is already linear, is unbiased. We computed the variance. Now we are going to prove another property. It is best in the sense that the variance of the least square estimate is less than the variance of any other linear unbiased estimate. So look at this now. I have a general linear unbiased estimate. I have a least square estimate which is linear and unbiased. So I am going to compare the least square estimate against all unbiased linear estimates. And that's one of the fundamental results in statistical estimation theory. And that theorem is called Gauss-Markov theorem. Gauss-Markov theorem, please remember, Gauss, a couple of hundred years ago, Markov, he lived in early 1900s. Gauss is of German origin and Markov is of Russian origin. So the theorem that characterizes the optimality properties of the statistical least squares. So what is that I need? I already have LUE. I want the B. I want the B in blue. The B in blue is characterized by the Gauss-Markov theorem. And we didn't have to do these things in the case of linear estimation, deterministic case, because there is no noise. There is no unbiased, there is only linear estimate. So in that case, we talked about linear, nonlinear estimates. Here we are going to be talking about linear unbiased estimate. We are going to have to talk about linear unbiased consistent estimate. We are going to talk about linear unbiased consistent and efficient estimate. So that's the idea here. So I'm now going to state and prove what's called the Gauss-Markov theorem, which essentially states that among all linear unbiased estimate, the least square estimate is the best. That means it's the least variance. So let x be an unknown being estimated. X is a vector, Rn. Now, I'm not going to estimate x, but I'm going to estimate a function of x. So I'm going to pick a mu, which is also an Rn vector, I am going to consider a function phi of x is equal to mu transpose x. So instead of estimating x, I am going to be estimating a linear functional of x. What is a functional? A functional is a mapping from vector to real. So x is a vector, mu is a vector, mu is constant. So phi of x is equal to mu transpose x. Now I am going to consider the problem of estimating phi of x. If I can estimate phi of x, I can estimate x. Why? By picking mu is equal to 1, 0, 0, 0, I can estimate x1. By picking mu, so what is this? This is by picking mu to be EI, which is the standard normal basis, which has 1 at position I, 0 elsewhere, mu transpose x, in this case mu transpose x is equal to xi. So by picking mu to be successively different unit vectors, I can estimate every component of x. So without loss of generality, I am now converting the problem of estimating a vector to estimating a scalar, the scalar being a linear functional of the scale of the vector mu transpose x. So consider the new problem of estimating phi of x. We are seeking a linear unbiased estimate of phi of x. To estimate this, I have the data z. So z is a vector. Please understand, z is a m vector, x is a n vector. I want to estimate phi of x, which is a real number. Phi of x is real. So I am going to use z. Z is a vector. So I want to be able to estimate the real number using a vector. That means first idea is to be able to convert the vector into a scalar. Therefore, I am now going to pick a vector A in Rm. I am going to consider the inner product of A transpose Z to be an estimator of phi of x. Please understand, there are a number of things. X is a vector, unknown. Z is a vector, observation about the unknown. I don't want to estimate the vector x itself, but I want to talk about a linear functional of x, which is mu transpose x. Z is the information on x, so I am going to consider a linear function on Z, which is A transpose Z. A is another vector. So mu is a vector, A is a vector, x is a vector, Z is a vector. Even though everything is a vector, I am going to be talking about estimating the vector phi x using A transpose Z. So if this is the estimator for phi of x, so phi of x is unknown, that's the estimator for the unknown. I am going to consider the expected value of this estimator A transpose Z, which is equal to expected value of A transpose Hx plus V, because Z is equal to Hx plus V. This is equal to A transpose H E of x plus A transpose E of V. E of V is 0. This is A transpose H of x. Now I want this estimate to be unbiased. So for A to the power of Z to be an unbiased estimate, only if phi of x is equal to mu transpose x, which is equal to expected value of A transpose Z, which is equal to A transpose H of x. Please understand the previous thing. Expected value of A of Z is equal to A transpose H of x. So that's the idea here. So mu transpose x must be equal to A transpose H of x. So I want these two to be equal. One way to make these two equal is to make sure mu transpose is equal to A transpose H, or mu is equal to H transpose A. Please understand, this is the condition for unbiasedness. So there is a mu, there is an A, and there is a H. So for the estimate A transpose Z to be an unbiased estimate of mu transpose x, these three quantities must be related to each other, that H transpose A must be equal to mu. Just to look at this now again. This is Rm, this is Rm, this is x, this is Z, this is mu, this is A, then I would like to be able to, this is H, this is H transpose. So H transpose A must be equal to mu. That's the idea. So H takes from N to M, Rn to Rm. H transpose takes from Rm to Rn. So this linear functional will be an unbiased estimate if and only if the constant vector A and mu I have chosen must stand in a linear relation, namely mu must be a linear transformation of the vector A. So that's the first condition. That's the condition for unbiasedness. Now, since it is unbiased, its mean square error is equal to variance. Please understand, we have already shown the mean square error is equal to variance plus the bias square. If it is unbiased, the bias is 0. So the mean square error is equal to the variance. So this is a scalar. The variance of the scalar is equal to the random quantity minus expected value whole square. So this is equal to A transpose Hx plus V minus A transpose Hx. So this comes from the previous analysis. This comes from Hx plus V. A transpose Hx, A transpose Hx will get cancelled. This is expected value of A transpose V whole square. Please understand, A transpose V whole square is equal to A transpose V times A transpose V. But you do know A transpose V is equal to V transpose A. So this is equal to A transpose V, V transpose A. So expected value of this is equal to expected value of that, which is equal to expected value of this, because A is a constant. But expected value of V, V transpose is R. So R is a matrix. A transpose RA is a quadratic function. Is a quadratic form of A. A is a M vector. So the variance of this is simply A transpose RA. So that's the next question. This is conditioned on it is unbiased. So this is the variance of the unbiased estimate, which is A transpose Z. Now we seek to minimize A transpose RA. Please understand, A transpose RA is the variance of my estimate. My A is not free. My A must be related to mu through this relation. So I want to be able to minimize this under the constraint H transpose A is equal to mu. Now please understand, I have already picked mu. I am going to be estimating mu transpose X. So I am now considering a vector A. So how should the vector A related to the vector mu? Unbiased condition essentially tells you H transpose A is equal to mu. So I would like to be able to minimize this where A is not a free variable. If A were to be a free variable, what is the minimum of X transpose AX? Is 0 at the origin. So the unconstrained minimum is not applicable. It's a constrained minimum is applicable because A is not a free variable. So among all A's that satisfy this constraint, what is the minimum of this? Now you remember that's a classical equality constraint minimization. Lagrangian multiplier technique applies. So I'm now going to fall back on the theory I have already developed. I'm going to consider a Lagrangian, which is the variables are A and lambda. So I want to be able to minimize A transpose RA. This is the constraint. So lambda transpose HA, H transpose A minus mu. That's a Lagrangian. This is the Lagrangian multiplier. So Lagrangian multiplier theory tells you by expanding the space over which the function is defined, I can convert a constraint minimization, equality constraint minimization problem to unconstrained minimization problem. So I have Lagrangian. I'm going to compute the gradient with respect to A, gradient with respect to lambda. There are m equations coming here. There are n equations coming in here. So I'm going to have to solve these two equations simultaneously. I'm assuming R is SPD. So by solving the first equation, I can get A is equal to 1/2 of R inverse H lambda. This comes from here. And H transpose A must be mu. So I substitute this A in here. So 1/2 of H transpose R inverse H lambda must be equal to mu. Therefore, lambda is equal to 2 times H transpose R inverse H inverse mu. Therefore, A, the optimal A is going to be this. R inverse H times H transpose R inverse H inverse mu. Please remember, mu is already, I have already picked. I already know H. I also have the nice properties R. Therefore, the vector A, using which I am going to convert the observation Z into a scalar as A transpose Z, the A must be picked like this. So if I pick A according to this formula, then I minimize the variance. If I minimize the variance, what is that? It is already linear. It is already unbiased. This is minimum variance. That becomes blue. That becomes blue. So the linear unbiased minimum variance estimate of phi of x is equal to mu transpose x, is equal to the estimate is A transpose Z. We just saw what is A. Go back to here. So I am going to take the transpose of this. That is equal to mu transpose H transpose R inverse H inverse H transpose R inverse Z. But this one, the one that is given in here, that's the least square estimate. The least square estimate for the weighted case. Least square estimate for the weighted case. Therefore, A transpose Z is equal to mu transpose x hat LFS. So we have now shown that A transpose Z is a good estimate, is an unbiased estimate, is a linear estimate, and its variance is also minimum, and the value of that estimate is given by that. Now, if mu is equal to 1, 0, 0, 0, 0, the best estimate of x1 is obtained. So this is equal to E1 transpose. So by picking mu to be E1 transpose, E2 transpose, E1, E2, E3, we can obtain different components of x. Therefore, I can estimate the entire vector x. Now consider two results. There is a note. If V is normally distributed with mean 0 and covariance R, the XLS is the best among all estimators. If V is not Gaussian, then there exist nonlinear estimates whose variance can be smaller than the linear estimate. So I would like you to be able to look at a couple of results. We have shown here, look at this now. What are the assumptions made in here? The assumptions made in here are that x is unknown, z is given. I'm going to consider a linear combination. So if I only know that V is such that E of V is 0 and the covariance of V is equal to R, using this information only, we have now derived the Gauss-Markov theorem, which says that among all the estimates, among all the linear unbiased estimates, the least square estimate has the minimum. Now, to say noise is such that E of V equal to 0 and the covariance of V equal to R, and to say V is equal to normal R, these two are two different things. I hope you understand that. In here, I only know the mean and the covariance. In here, I know the entire distribution normal. So Gauss-Markov theorem was proved under this assumption. Rao, C.R. Rao, as I told you earlier, in his book 1973, and in collaboration with another very well-known mathematician, statistician Blackwell, they proved a theorem which is called Rao-Blackwell theorem, in which they proved that if V, in addition to being mean zero and covariance R, if it is also normal, then the least square estimate is the best among all other estimates. If V is not Gaussian, then there exists estimates whose variance can be smaller than the linear estimate. There exists nonlinear estimate can be smaller than the linear estimate. That means we are trying to admit some bias to be able to get lesser variance. So that again talks about the bias, the trade-off between variance and bias. This is the theory of Gauss-Markov theorem. It is described in our book. It is also described in the book by Meltzer and Cohen. And this book is available, I think, at the IIT library. Decision Estimation Theory is a great book to be introduced to basic aspects of statistical estimation. That's of great relevance to data science.